Albert Einstein, a name synonymous with genius, but he wasn't a lab-bound eccentric. He was a curious soul, fascinated by the universe from a young age. He pondered simple questions with profound implications. What would it be like to ride a beam of light? Could gravity really be a force acting at a distance? These musings led to a revolution in physics. Einstein, with elegant simplicity, shattered our Newtonian view of a static, absolute universe. He showed us a reality far stranger and more wonderful than we could have imagined. His theories, born in thought experiments and scribbled equations, redefined our understanding of the cosmos. They revealed a universe where time is fluid, space bends, and energy and matter are two sides of the same coin. Einstein's legacy is not just scientific, it's a testament to the power of human curiosity and the elegance of the universe itself. Einstein's work on relativity is actually two theories, special relativity and general relativity. These groundbreaking theories have fundamentally changed our understanding of the universe. Don't let the names fool you, they are both profoundly important. Each theory has its own unique implications and applications that have revolutionized science. Special relativity, published in 1905, deals with the relationship between space and time. It was a radical departure from the classical mechanics of Newton. It tells us that the speed of light is constant, no matter how fast you're moving. This principle has been confirmed by countless experiments. This has some bizarre consequences. For instance, time itself is not absolute. Time slows down as you approach the speed of light. This phenomenon is known as time dilation. This isn't science fiction, it's been experimentally verified. Particle accelerators and GPS satellites provide real-world evidence of these effects. Special relativity also gave us the famous equation E equals mc squared, which we'll explore later. This equation shows the relationship between mass and energy. General relativity, published in 1915, is even more mind-bending. It expanded on special relativity to include gravity. It's Einstein's theory of gravity. This theory has been confirmed by observing phenomena like gravitational waves. Where Newton saw gravity as a force, Einstein saw it as the curvature of space-time caused by mass and energy. This was a revolutionary idea at the time. Imagine a bowling ball on a trampoline distorting the fabric. This is a simple analogy to understand how mass affects space-time. That's how massive objects warp space-time, influencing the motion of objects around them. This warping explains why planets orbit stars and why light bends around massive objects. One of the most startling revelations of Einstein's theories is that time is not absolute, it's relative. This means that the way we experience time can change based on various factors, which can be quite mind-boggling. Time is not a universal metronome ticking at the same rate for everyone everywhere. Instead, it can stretch or compress, depending on where you are and how fast you're moving. Instead, time is experienced differently, depending on your relative motion and the strength of the gravitational field you're in. For instance, astronauts in space experience time slightly differently than we do on Earth. This phenomenon is called time dilation. Time dilation means that time can actually slow down or speed up depending on your velocity and gravitational environment. Imagine two identical clocks, one on Earth and one on a spaceship traveling at a significant fraction of the speed of light. The clock on the spaceship will tick more slowly. According to special relativity, time will pass slightly slower for the clock on the speeding spaceship compared to the clock on Earth. This effect becomes more noticeable as the spaceship's speed increases. The faster the spaceship travels, the more pronounced the time difference becomes. This means that astronauts traveling at high speeds could age more slowly than people on Earth. General relativity adds another layer to this. It tells us that gravity can also warp time. Gravity also affects the flow of time. The stronger the gravitational field, the slower time moves. A clock near a massive object like a black hole will tick slower than a clock further away in weaker gravity. This means that time near a black hole is significantly slower compared to time on Earth. Time, it turns out, is far more flexible than our everyday experience suggests. It bends and stretches in ways that challenge our understanding, making the universe a much more fascinating place. Section 4. The fabric of reality, space-time. Before Einstein, we thought of space and time as separate entities. Space was the stage and time was the universal clock measuring events unfolding. Einstein shattered this illusion. He showed us that space and time are inextricably linked, forming a four-dimensional fabric called spacetime. Imagine a vast, flexible sheet. This sheet represents space-time. Now place objects of different masses on this sheet. A marble representing a small object might create a tiny dip. A bowling ball representing a massive star would create a much larger distortion. This is how gravity works in general relativity. Massive objects warp the fabric of space-time around them. This warping is what we experience as gravity. It's not a force acting at a distance, it's the curvature of space-time itself that dictates how objects move. Section 5. Unlocking Energy's Secret, E = mc2. Perhaps the most famous equation in history, E=mc2, represents a profound insight into the nature of energy and matter. This simple yet powerful formula, introduced by Albert Einstein in 1905, revolutionized our understanding of the universe. In this elegant formula, E stands for energy, M for mass, and C for the speed of light, approximately 300,000 kilometers per second. The speed of light is a constant, a fundamental aspect of the universe that links mass and energy in a way that was previously unimaginable. The equation tells us that mass and energy are equivalent and interchangeable. This concept, known as mass-energy equivalence, means that mass can be converted into energy and vice versa, a principle that has profound implications for both science and technology. A small amount of mass, when multiplied by the square of the speed of light, an incredibly large number, represents a tremendous amount of energy. This relationship explains why even a tiny particle of matter can release an enormous amount of energy when converted. This equation revealed the vast energy locked within the nucleus of an atom, paving the way for the development of nuclear power and, unfortunately, nuclear weapons. The realization of this energy potential has had both beneficial and devastating consequences for humanity. Albert Einstein is a cornerstone of modern physics with implications far beyond its initial scope. It has influenced various fields from particle physics to cosmology and continues to be a fundamental principle in scientific research and technological advancements. It underpins our understanding of nuclear reactions, the processes that power stars and the very early universe, where energy condensed into matter, forming the building blocks of everything we see around us. This equation not only explains the energy production in stars, but also provides insights into the origins of the universe itself, making it a key to unlocking the mysteries of existence.